Hi there, my name is Dino. I was born in Piraeus in Greece. My early days, what great days. I was a naval officer, and in that capacity, I was lucky to be taught the art of sailing by some old wolves of the sea. It is then that I notice their ambivalence about the role of the straight boom and its effect on the total rig. In fact, their concern was that although the boom had an essential role to play in stabilizing the sail, at the same time, because of its rigid straight shape, it was deforming the flow of air around the sail on the lower part. Sails manufacturers, worried about all this, have developed sophisticated concave services and management techniques to minimize the loss that nevertheless remains significant. So I would like to share with you in this video an idea as to how one can go about tackling this insurmountable conflict around the boom in a manner which is simpler, more efficient and more reliable. The idea is not really rocket science, but you might find it useful in the way you go about sailing. So first, let us look at the best practice today. The photo illustrates how the main sail is typically arranged. The configuration of the profile and its angle of attack is crucial for the specific propulsion power. Maximum driving force is produced in the middle and the upper part of the sail. In the lower part, the flow is increasingly deflected and ultimately interrupted by the turbulence produced by the straight boom. Neither the angle of attack, nor the luff zone, nor the outflow angle on the leach are directed to the angle of attack of the boom. In conclusion, there is a serious work turbulence problem at the foot of the sail, which is caused because of two main reasons. One is the pressure differential between the two sides of the sail at its foot, and the other is the one described above because of the straight boom and the deformation of the sail. So now this is what we propose as a remedy. An innovative generic concept as illustrated. It consists of a semi-rigid boom with a capacity to bend under considerable load as the body of a bow, an expansion rod placed eccentrically as the arrow, and Y-string that allows the bending process. The photo highlights the generic concept of the innovation. The boom can acquire any value of the camber and remain at that position with adequate residual rigidity to absorb instability forces on the sail. A flat sail is attached to this boom in the usual manner. The kicking strap, in combination with the main sheet, ensure a tensioned leach line. With this, the sail, with a bent boom, assumes its optimum airfoil shape on all its height, including the boom itself. The rod expansion system utilizes various simple technologies in order to tackle various circumstances, such as hydraulic cylinders or worm-threaded rods. So let us now move into a full-scale demonstration. The example I have used is composed of closed-circuit hydraulic ramps to drive the rods. First, some technical design. So you can see on the drawing the package of the expansion rods is shown in detail. For reasons of space economy, the expansion rods are not straight. That way, the left side expansion mechanism occupies minimum space. We will now see the pilot system in operation. It simulates a boom for a boat of 45 feet. The material used for the boom is aluminum, but more advanced materials would be preferable because they will succeed a better ratio between the load required to bend the boom and the residual rigidity to keep the stability of the sail. In addition, it provides better fatigue performance. We start with the boom amidships. The expansion strings are attached at the rear and the position where the main sheet is hooked. The boom bending gear is close to the mast. A closed-circuit hydraulic cylinder on each side of the boom drive a corresponding expansion rod. The expansion strings, driven from aft, are passed through the tip of the expansion rod and end at the forward end of the boom. So, after this introduction, we are now ready to see the boom operating on the starboard tack first. Energizing the hydraulic cylinder, the extension rod is gradually extended, and with the attached string tensioned, the boom is bent at increasing camber. It stops at any point. It is stable with adequate rigidity to allow stability of the sail. As said earlier, this shape of the boom, close to a perfect airfoil, with the leech line tensioned, will force the whole surface of the sail to take a similar shape. The position of the expansion rod ensures not only the magnitude of the camber, but also the center of effort of the sail, as it can move beyond its maximum extension on the aft side. To complete the presentation, let us see a similar operation of the boom on the port side. The versatility of boom positioning and the consequent sail performance are identical to the starboard side. So the proposal satisfies the need for the sail and the boom to acquire airfoil shape on both sides. Two additions to the proposed package will enable us to take full advantage of the flexible boom's capabilities. The first is a modular flexible skirt under the boom with an open T-profile inversed. This is shown in this graphic presentation. The skirt construction, composed of modular interlinking elements, enables it to follow the varying camber of the boom whilst maintaining continuity. The skirt is a valuable add-on to the sail surface, in particular wind conditions, but more importantly, the inverse open T-profile essentially eliminates most of the wake turbulence caused by the pressure differential of the two sides of the sail. Finally, in its complete form, the system includes a computerized control of the value of the camber system, through which, of course, we obtain an optimum performance of the sail. It is worth noticing the inherent advantages of FBSS. We can detect easily. Firstly is a flat sail and the potential to use modern material for it. Then is a radical simplification of the rigging and operating around the main sail. It follows that the relatively boat righting couple is reduced due to lower sail center and acquisition of sharper tacking behavior due to an increase of the surface of the sail under linear flow, which of course calls for a smaller balance for it, lesser heeling due to smaller righting couple, lighter boat due to the need for smaller ballast, faster vessel due to increase of power, reduced weight and drag, and finally safer boat due to smaller relative righting couple. The proposed system requires minimum electrical power, as well as small amounts of stored energy, and none, of course, in case of manual handling. The whole system can be controlled from the cockpit. It can be applied in existing boats with minimum changes without disturbing the rig of the rest of the system. Thank you very much for watching this presentation. I hope you found something very interesting. We're looking for partners to help us develop further the concept. We have applied for a European patent in the meantime. If you're interested, please contact me on my email address, dino@optir.eu, that you find in the slide that follows. Thank you.